Alright, section 4.8 is introducing the antiderivative. And so we have a definition of an antiderivative. So we're going to call this antiderivative capital F. So capital F is going to be an antiderivative of little f. And the way we're going to test that is if we can take the derivative of the antiderivative and get back to the original little f, then we know it's an antiderivative. So, and it should work for all x values. Okay. So we're not going to have rules, antiderivative rules outright just yet. We're just going to kind of talk about the concept of an antiderivative. So, for example, the directions will say find the antiderivative capital F. Alright, so we're going to start off with little f as a polynomial, okay, 12x squared. Now, the relationship is we have to come up with a capital F that when we differentiate this, when we differentiate capital F, we get back to little f, okay. So the general antiderivative, remember when we differentiate, we bring the power down, multiply it times the constant, and then subtract 1 from the power. So if little f has an x squared, the antiderivative should have an x cubed, right? So when I differentiate x cubed, I'm going to get 3x squared. But I don't want 3x squared, I want 12x squared, and so I'm going to put a constant here of 4x cubed, right? So when I differentiate 4x cubed, I get 12x squared. Now, with a general antiderivative, we always want to add a constant, okay? Because the derivative 4x cubed is also 12x squared, because when we differentiate a constant, it goes to 0. So let's try another one. Okay, another polynomial here. Alright, so here's my little f. So if I wanted to find the antiderivative, I'm just going to take each term individually. So 8x cubed, the antiderivative needs 1 power higher than the x cubed. So I know it needs to be x to the 4th. And if I differentiate x to the 4th, I'm going to get 4x cubed. But since I need an 8x cubed, I'm going to put a coefficient of a 2 here. So the derivative of this term is now 8x cubed. So I'm going to move on. Okay, I'm going to go ahead and bring down the minus sign. This next term, the power of x needs to be 1 higher. So x squared. If I differentiate x squared, I get 2x. Okay, or if I differentiate negative x squared, I get negative 2x. So this term doesn't need a coefficient. So I already have the derivative of capital F is the first 2 terms of little f. So this 5 is a constant. It really has x to the power of 0, although we don't write it. So I know that this term needs to be 1 power higher. So I'm going to put an x to the first power. So if I differentiate x, I'm going to get 1, but I don't want 1, I want 5. So I'm going to put 5x here. And the derivative of 5x is indeed 5. Okay. And as with all antiderivatives, I need to add a constant. So if I were to differentiate capital F, okay, capital F prime is little f, and therefore capital F is the antiderivative of little f. All right, so let's think about other functions that we can find the antiderivative of, such as trig functions. Right? So if little f was sine x, then we need to remember what the function is, that when we differentiate we get sine. Okay, so the derivative of cosine is negative sine. So if I put negative cosine here, the derivative of negative cosine is sine. And as always, add a constant, because when we differentiate a constant it goes to 0. So if I were to find capital F prime, I would get little f. Right? So another trig function, if little f was negative cosecant cotangent, right? You should recognize that, right? Negative cosecant cotangent is the derivative of some trig function. So if you remember, negative cosecant, negative cotangent is the derivative of cosecant. So the antiderivative is cosecant x plus c, right? Because if I differentiate capital F, I get little f, because the derivative of cosecant is negative cosecant cotangent, and the derivative of c is 0. So another function that we can find the general antiderivative of is this function. Right? So we're not going to undo the quotient rule here. Undoing the quotient rule will require partial fractions, right? But this is in a form that we can come up with really easily, and the relationship between the numerator and the denominator is key here. So the denominator is x squared and the numerator is 2x. So if you notice, the numerator is just the derivative of the denominator. So this is kind of the form f prime of x over f of x, right? And so if you can see that, then what function did we take the derivative function over the original function? And that would be an ln, right? So this would be, the antiderivative would be ln of x squared, right? Because when we differentiate ln, we take the derivative of the argument over the argument, and then plus c. So I didn't cancel the x's here because it's easier to see the ln function, but if you see anything with a relationship of the derivative of the denominators and the numerator, it is an ln function, right? So one more here. Right? This is something that we can find the antiderivative of as well. So you notice we have an e, and the derivative of e to the x is just e to the x. But when we have e to the x cubed in here, the derivative of e to a function of x remember, if we differentiate this, we're going to get e to the function of x times the derivative of f. So if you notice, this front part here, 3x squared, is just the derivative of x cubed. Okay, so it fits this form of e to a function times f prime. So the antiderivative is going to be what's inside here, right? Here's my antiderivative. So if I differentiate the antiderivative, I get back to the original. So we're going to put e to the x cubed here plus c, right? So if I take capital F prime, I'm going to get e to the x cubed times 3x squared plus 0, which is exactly what the original little f was equal to. So in a nutshell, you should be able to find the antiderivative of like simplistic trig functions, polynomials for sure. Ln's occur in this section, as well as exponential functions, right? So just one more because I thought about it. Alright, so if we had this exponential function 2 to the x ln of 2, you should recognize that as the derivative of 2 to the x. Okay, so the antiderivative of 2 to the x ln of 2 is simply 2 to the x plus c. Because if I were to take the derivative of capital F prime, let me just put a because here, is going to be the derivative of 2 to the x, which is 2 to the x ln of 2 plus 0, which this equals little f. Okay, so the derivative of capital F is little f, and therefore we know we have the correct antiderivative. All right, so now we're going to look at finding an antiderivative without the constants, and the only way we can do that is if we're given some points on the original function that we can plug back in. Okay. So the directions are going to say something like find f of x if we're given the second derivative of f of x. And we're also going to be given 2 points here. We know that f of 0 is 4 and f of 1 is 1. Okay, so we weren't given f of x, we were given the second derivative of f of x. So if I find the antiderivative of f double prime, I'm going to get f prime. If I find the antiderivative of f prime, I'm going to get back to f. But it's going to create some constants in there, right? So if we want to find f of x without those generic constants, that's where these points come handy, and we're going to plug those points in to solve for those constants. So I'm going to rewrite f double prime here. So if I find the antiderivative of f double prime, that's going to be f prime. Okay. So the antiderivative of 12x squared plus 6x minus 4. I'm just going to take it one term at a time. Okay, so the antiderivative of 12x squared needs an x cubed because the power increases by 1. If I differentiate x cubed, I get 3x squared, but I don't want a 3x squared, I want a 12x squared. So if I multiply x cubed times 4, then the derivative would be 12x squared. So moving on to the next term, the antiderivative is going to have 1 power higher, right? And so in order to get 6x, I really need to put a 3 here, right? Because the derivative of x squared is x, but if I put a 3 out in front, 2 times 3 is 6, subtract 1 from the power, it gives me 6x. Okay, so the derivative of 3x squared is 6x, so I know this part of the antiderivative is correct. Right? The antiderivative of a constant, we're going to do the constant times x, right? Because the derivative of negative 4x is negative 4. And then we also have to remember to add c, right? So now to get to f of x, I'm going to do the antiderivative of f prime of x. So finding the antiderivative one more time. Right, so the antiderivative of 4x cubed needs 1 power higher, right? So I'm going to increase the power of x by 1, and then I don't have to add a constant to this one because the derivative of x to the 4th is 4x cubed. So we're good there. Okay, for the next term, I'm going to increase the power by 1, and again, this one doesn't need a coefficient because the derivative of x cubed is 3x squared. The antiderivative of 4x, I need to increase the power by 1, right? So we go from an x to an x squared. The derivative of x squared is 2x, and I want a 4x, so I'm going to throw a coefficient of 2 in there, right? So derivative of negative 2x squared is indeed 4x. Now, what's the antiderivative of c? Well, it's times, this is just a constant, right? So this is x to the 0 power. So if I increase the power of x on this term 1, I'm going to get x, right? Now the derivative of x is 1, but I really want a c there. So the derivative of cx would just be c, okay? And then another general constant needs to be added to this, okay, to account for a constant that goes to 0 when you take the derivative, and so I'm just going to add d, right? So the derivative of x to the 4th plus x cubed minus 2x squared plus cx plus d is f prime, right? And the derivative of f prime is f double prime. So here is my f of x, right, in general. So we have these constants here, and we want to find f of x without those constants, and so that's where this point, these points come in handy. So I like to plug 0 in first, because that's going to allow us to get rid of basically all the terms except for d, right? So if I plug 0 into this function, okay, I'm going to get 0 to the 4th plus 0 cubed minus 2 times 0 squared. I know you could see this, but, all right? So f of 0 is basically d, okay? But what should f of 0 equal, right? F of 0 should equal 4. So that means d is 4. Okay? So I know what this constant is. So now I know f of x with the d. So I'm going to rewrite it. All right, so here's my f of x. It still has a constant c. And so if I use the other point and plug 1 into this, that will help me solve for c. Okay. So if I plug 1 into the function, I'm going to get 1 plus 1 minus 2 plus c plus 4. Okay. Now all of this, f of 1 should equal positive 1. So I'm going to go ahead and simplify this. 6 minus 2 is 4. So I basically have c plus 4 equals 1, because f of 1 should equal 1 according to the point I was given. And so that forces c to be negative 3. Okay. So now I know what this constant is. Right? So f of x is x to the 4th plus x cubed minus 2x squared minus 3x plus 4. And a way to check this is to go ahead and take the derivative twice and make sure you get back to what f double prime should equal. All right, so as a check, I'm just going to go ahead and find the first and the second derivative. All right, I'm going to get 4x cubed plus 3x squared minus 4x minus 3. And then if I take the derivative of that, I get 12x squared plus 6x minus 4. And the f double prime matches the original f double prime, so I know my answer is correct. Okay. So if you're given some points, that means that you need to find these general constants that we add to the end of those antiderivatives. All right, so I'm going to give you the fundamental theorem of calculus. All right, it has 2 parts. Now, 4.8 doesn't really go over it in depth, but 5.2 and 5.3 do. And so we are going to kind of just take it at face value for today. And then just know in 5.2 we're really going to dive into what the fundamental theorem of calculus means. Right? So the first part, the fundamental theorem of calculus. Part 1. Okay. All right, so instead of writing the fundamental theorem of calculus, I usually just call it the FTOC. Okay, so this is the FTOC part 1. So part 1 defines the integral as the antiderivative. And so if you can just kind of hold on to that fact, you will be good. So we're going to I'm going to give you the whole definition here, and it's going to seem confusing, but just know in 5.2 we're really going to dive into this. So we have to have a continuous function. So our g of x function is going to be the integral from a to x of some function with respect to t. Now I know the fact that these are t's and these are x's is confusing, right? But we're going to talk about that in 5.2. But do notice that the x's here are the same x's, right? So this function g is the antiderivative of little f. Okay, which is to say that the derivative of g is little f. So if I could, okay, just a little y, if I start with that equation, g of x equals the integral from a to x of f of t dt. All that you really need to understand is if I take the derivative of this equation, the derivative of g of x is g prime, right? And the derivative of an integral is the function, right? Now, we're going to change f, okay? It's not going to be f of t, it's going to be f of x, because this integral is really with respect to x here. So what I really just need you to know is that the derivative cancels out the integral. And we're going to get f of x, right? So let's just look. This is called an indefinite integral. Usually we don't have the a to the x and the f of t here. If we just have an integral symbol without any variables here, we would just say, what's the integral of 12x squared plus 6x minus 4. Okay. Well, the integral, okay, is the antiderivative. Okay, the integral is the antiderivative of this function, right? Because g is the antiderivative. So this is what we call an indefinite integral. And so the integral of 12x squared plus 6x minus 4, we just need to find the antiderivative. So the antiderivative of, one term at a time, the antiderivative of 12x squared is increase the power of x squared by 1, right? And we get x cubed. The derivative x cubed is 3x squared, but I want 12x squared, so I'm going to add a 4 here. And then the antiderivative of 6x is increase the power by 1 again. Okay, so x squared, but I need to add a 3 there in order to get 6x. And the antiderivative of 4 is minus 4x plus c. Okay, so this is g. Okay, g of x equals the integral. Okay, so this is g of x, the antiderivative. So as a check, okay, as a check, if you were to differentiate this function here, okay, the derivative of g, I'm just going to write as g prime. The derivative of the other side is 12x squared plus 3x minus 4. Notice that 12x squared minus 3x minus 4 is this integrand here, right? So therefore, we got the function back out, okay? So just know that the integral is the antiderivative, right? So let's go ahead and do the integral of cosine x dx, right? And we just want to know what the antiderivative of cosine is, right? So what do we need to differentiate to get cosine? Of course, it's sine plus c, okay? All indefinite integrals need a constant. A constant of integration, that's what it's called. Right? So if it's an indefinite integral, meaning we don't have any numbers here, we're always going to add c. Right? So it's just another way of kind of giving you an antiderivative problem. Right? So let's look at the antiderivative of 3x squared plus 5 over x cubed plus 5x. Right, the dx is just telling you it's the antiderivative with respect to x. Okay, so it's kind of like your variable of integration instead of your variable of differentiation. Right. So do you recognize the pattern here? Okay, we're not going to undo a quotient rule here. To find the antiderivative of this, you just need to recognize that the derivative of the bottom is up top. Right. So this is an f prime over f function, which fits our ln, okay? So the antiderivative of this is going to be ln of x cubed plus 5x plus c. Because if I were to differentiate, if I were to do the check and find the derivative of this function, I would get the derivative of the argument over the argument, and the c would go away, right? So as a check, you can always just differentiate your answer and see if you get back to this integrand. All right, so a few more that we didn't talk about on the first page. We can do this one. And so it's just a matter of, do you recognize this integrand? Okay. Negative 1 over the square root of 1 minus x squared. It should ring a bell. Okay, we differentiated a function and got this. Right? So the function that we differentiated to get this was arc cosine. So the antiderivative arc cosine plus c would be the correct answer, right? Because the derivative arc cosine was the negative 1 over square root. The derivative arc sine was the positive 1 over the square root. Right, and this one didn't have like a chain rule built into it, so just to make it easier to spot. Okay, so one of the more popular integrals that a lot of our functions are going to fit into is this one. In Calc 2, they love this integral. A lot of things we could fit into this form, right? And so this was the derivative of some function, okay? And so if you remember, the derivative of arctan was this fraction. So the antiderivative would be arctan x plus c, because if I were to differentiate arctan, I would get 1 over 1 plus x squared, right? So the just to wrap up part 1, okay, it's just defining the integral as an antiderivative, right? And it's going to, you know, if you differentiate an integral, they cancel and you get the function back out, right? So moving to the fundamental theorem of calculus part 2. I'm just going to call it the FTOC. Again, we're going to have a continuous function. And we're going to integrate from a to b. This is called a definite integral, right? Notice there's no coefficients here. These are just the endpoints of this interval here. So if we integrate from a to b, f of x dx, right? So an integral is the antiderivative, but when we have numbers here, we're going to evaluate the antiderivative at b minus the value of the antiderivative at a, where f is any antiderivative little f. Now they say any antiderivative because we can add generic constants. So 3x squared plus 2 is an antiderivative, 3x squared minus 1 is an antiderivative, right? We can change those constants. So we're going to take into consideration any constant that's added to that antiderivative, okay? So this is called a definite integral, right? So let's go ahead and calculate a definite integral, okay? So let's integrate from 2 to 5 this polynomial. So the first thing you want to do before you jump into doing the antiderivative evaluations is go ahead and just find the antiderivative of 3x squared minus 2x plus 4. So the antiderivative, the general antiderivative, okay, of 3x squared minus 2x plus 4. So I'm going to anti-differentiate each term individually. So the first term needs an x to the cube because we always increase the power by 1. Okay, the derivative of x cubed is 3x squared, so we don't need to add a constant or a coefficient. All right, minus x squared, right? The derivative of minus x squared is minus 2x, so that term is good, plus 4x, because we need to add an x to a higher power here. The derivative of 4x is 4, and so we're good there. I'm going to go ahead and add a c, okay, for that any antiderivative. Now, this is my antiderivative, and I want to evaluate that. So evaluate is usually indicated with a vertical line, and we want to evaluate that from 2 to 5. Right? So the fundamental theorem of calculus part 2 says we need to evaluate the antiderivative at b, which is the top number, minus the antiderivative evaluated at a, which is the bottom number, right? So I am going to plug 5 in first, right? So I'm going to get 5 cubed. I'll go ahead and write down the number. 5 squared, 4 times 5, and then the c. So here's my antiderivative evaluated at 5. And then I want to subtract from that the antiderivative evaluated at 2. So 2 cubed is 8, minus 2 squared, plus 4 times 2, plus c. So if I simplify this, okay, and kind of combine my like terms, I'm going to get 120 plus c. out of that first parentheses. Out of the second parentheses, we're going to get 12 plus c, but if I distribute the negative sign, I'm going to get minus 12 minus c. Right, so what's important here is that the c's are going to cancel, right? C minus c, they cancel. Right? And so I get a final answer of 108. Right? So no matter what constant we add here, okay, this is just a general constant, but if I would have added 1 or negative 3 or 4, right, when we evaluate the antiderivatives, one minus the other, that constant, whatever it is going to cancel. So for this reason, when we do definite integrals, we usually don't put the plus c in our antiderivative because they are always going to cancel, right? So the antiderivative of this function from 2 to 5 is 108. We're getting a number, right? So what does that number represent? Okay, that number right here represents an area under this graph. Right, so if I were to graph 3x squared minus 2x plus 4, I'm not going to get the exact graph, I'm just kind of make this up here. But this is a quadratic that opens up. Okay, so if I just draw a general quadratic like so, okay, and if I were to look at the integral from 2 to 5, I'm just going to make this 2 here and this 5 here. If I were to calculate this area here between the curve and the x-axis, this area is going to equal 108 units squared, right? Because area is usually squared. And so it's just calculating the area between the curve and the x-axis. Right? So let's do another one. Let's integrate from 0 to pi a trig function here. Right? So our variable of integration is theta. Right? So we want to find the integral from 0 to pi of cosine theta minus 5 sine theta. Well, the first thing is to come up with the antiderivative. Right? So one term at a time, the antiderivative of cosine. What function do I need to differentiate to get cosine? Well, that's sine, of course. Right? So the derivative of sine is cosine, so we're good there. Right? And then we need to get minus 5 sine. So what function gives us a minus sine? And that would be cosine, but of course we need that 5 there. Okay, so it's 5 cosine theta, but just check it, right? The derivative of 5 cosine would be 5 times negative sine, which is indeed that second term there. Okay, so here's my antiderivative. I'm not going to put a plus c because we have a definite integral, and we just want to evaluate this from 0 to pi. Right? So I'm going to plug these numbers in. Okay. The top value minus the bottom value. Right? So if I plug pi in first, we're going to get sine of pi plus 5 times cosine of pi minus, and then we want to plug 0 into our antiderivative as well. So sine of 0 plus 5 times cosine of 0. Right. So I'm just going to pick some points on the unit circle here to evaluate these. 0, of course, has the point on the unit circle 1, 0, and pi has the point negative 1, 0, right? And so sine of pi is the y-coordinate here, so this is 0. Cosine of pi is negative 1, so I'm going to get minus 1 here. And then sine of 0 is 0. So I'm going to kind of cancel that out. Cosine of 0 is 1, so I get 5 here, but when I distribute the minus 0, minus 5, go ahead and write that. is, oops, yeah, I forgot to multiply my cosine times 5, right? So this shouldn't be a 1, this should be a 5. All right, okay, that's better. So I'm going to get, basically as an answer, negative 10, okay? Now, how is that possible? How do you get an area that is negative? Okay, so again, I didn't bring my calculator in here, but if I were to graph cosine minus 5 sine, right, it's kind of like a trig function. So I'm going to kind of do something like this, okay, and call this 0 and call this pi. Okay. So what happens is that the area above the x-axis is counted as negative, and the area below the x-axis is counted as negative. So when your integral is negative, that means there's more area below the x-axis than above, right? So I'm just going to write that, right? There is more area below the x-axis than above. So negative integrals is possible. It's just calculating the area under the curve. Okay, so let's go ahead and find the integral using geometry. Right? So I'm just going to write a statement here. So the definite integral is a calculation of the area under the curve, right? So using geometry, okay, we'll use the antiderivative next. Right? But if I wanted to calculate this using geometry, right, I want to find the area under this curve from 0 to 2. Okay, so I'm going to go ahead and go and graph this function. X plus 1 from 0 to 2. So if I plug 0 into this function, I get 1. If I plug 1 in this function, I get 2. If I plug 2 into this function, I get 3. Right? So here is my line, right? X plus 1. And I want to find the area between 0 and 2, okay, between the graph and the x-axis. So this is a straight line, which makes a really nice geometric figure. Okay, so if I were to break this down, I would probably do a triangle on top of a rectangle. Okay, so I'm going to find the area of this triangle plus the area of this rectangle. Right, so the area of the triangle, base is 2, height is 2, so the area of the triangle is 1/2 base times height. Okay, so we're going to get half of the base 2 times the height 2, which is basically 2, right? Plus the area of the rectangle. The rectangle is length times width. The length is 2, the width is 1, and so we're going to add 2, and so we get an area of 4. Okay, so we can calculate this area geometrically. Now this area should match up with the fundamental theorem of calculus, doing the antiderivative and evaluating the antiderivative at the top minus the bottom. So let's go ahead and show that. Okay. So what is the antiderivative of x plus 1? So I know I need to increase this power by 1. So this is now going to be x squared. Right? Now the derivative of x squared is 2x. And I don't want 2x, I want 1x. So if I multiply this by half, okay, the derivative of 1/2 x squared is 1x to the first, right? Plus the antiderivative of 1 is x, and we're going to evaluate that from 0 to 2. Right? So I'm going to plug 2 into the antiderivative first. So we're going to get 1/2 times 4 plus 2 minus, and if I plug 0 into the antiderivative, I just get 0. Right? So half of 4 is 2, 2 plus 2 is 4, okay, and the 2 match up. Right? So the definite integral equals the geometric area under the curve of x plus 1. Okay. So let's do another one. We're just kind of estimate it. Okay. So geometrically, I would like to find the area under this graph. Now this graph is curved, so our geometric answer is just going to be an approximation, but if we do it carefully enough, we'll get a pretty good answer. Right? So we want to go from 0 to 4. 1, 2, 3, 4. 1, 2. All right. So the area, or the graph, is going to go through 1, 1, and 4, 2. And it's going to look like a square root, like so. Okay. So this is a curved function, right? So I'm going to kind of put some grid lines on here. If this was on graph paper, or as if it was on graph paper, just to kind of see the blocks. Okay. So, and I want to find the area between the curve and the x-axis. So it looks like we have 3 whole blocks here, right? So we're going to find the area of each block here. So I'm going to put 1 here, and 1 here. Now, this area of this block, this line is kind of almost diagonal, right? So it looks like this area here would be like half of the block, if you will. So I'm going to estimate it at 0.5. Okay. Now, this area here is just a small sliver. So, is it half? Half would be here. It's kind of like a quarter, or maybe even less than a quarter. So I'm going to put 0.2, right? Instead of 0.25, right? Now, this area here, if I were to cut this in half, it's a little bit, there's a little gap above here, but there's also a little gap down here, so I'm going to put 0.5 for this one as well, like it's half of the area, right? And this one is more than half, maybe like 0.7, okay? So I'm just kind of guessing. So if I add all these numbers up, 1 plus 1 plus 1 plus 0.5 plus 0.2 plus 0.5 plus 0.7, 4.9, right? So I'm getting 4.9 units squared. Maybe it wasn't the best graph, but if I were to estimate the area geometrically, I would say 4.9 units squared, right? So let's go ahead and use the antiderivative, right? So how do we antidifferentiate a square root? Because we haven't done that yet. Well, you change the square root to the 1/2 power. Okay? And so then when we do the antiderivative, we just need to add 1 to 1/2, right? So we're going to get 3/2. Right? If I add 1 to 1/2. Now, the derivative of x to 3/2 is 3/2 x to the 1/2. So I don't want a 3/2 here. So if I put the reciprocal of that, 2/3, okay, and then when I pull the power down and multiply it, 3/2 times 2/3 is 1, right? So this is my antiderivative, and I want to evaluate that from 0 to 4. So plug the 4 in first. We're going to get 2/3 times 4 to the 3/2 minus, if I plug 0 in there, I'm just going to get 0. Right? So 4 to the 3 halves, 4 cubed is 64. 64 to the 1/2 power is 8. Right? So I'm going to get 2/3 times 8, which is basically 16/3. Right? 5 and 1/3. So the actual area was 5.333, so I was off by a bit, but as you can kind of see the correlation there. Right? So just one more, actually probably two more. Okay, two more examples here. Okay, the integral from 0 to 2 pi of sine x. Okay, let's do it geometrically first. All right, so I want to graph sine x from 0 to 2 pi. All right, so as you can see, the sine curve goes something like this, right? Now, instead of kind of breaking this apart geometrically, I think we can agree that the area above the graph equals the area below the graph, and the area. So these shapes are equal, and the area above the graph is positive, and the area below the graph is negative. So I'm going to say that this area is going to be 0, right? Because they're going to cancel each other out. So let's go ahead and evaluate that, okay, using the fundamental theorem of calculus and finding the antiderivative and evaluating the antiderivative from 0 to 2 pi. All right, so the antiderivative of sine. The derivative of cosine would be negative sine. So if I put a minus out in front of here, the derivative of negative cosine is positive sine, and I want to evaluate that from 0 to 2 pi. So I'm going to plug 2 pi in first. So I'm going to get negative cosine of 2 pi minus negative cosine of 0. Right. So remember what cosine of 2 pi and 0 are. Right, so 2 pi is here, cosine is the x value, so we're just getting 1. So we're going to get minus 1 minus another minus 1. So negative 1 plus 1 is 0. Right? So an integral is the area under the curve. Right? So I just want to do one more geometric example for you. So this is going to take a little bit of time to plot, but I think it'll be helpful. I think your final exam question is very similar to this one. So the first point here, I put wrong, but I'll just go with it. Didn't copy my graph right. Okay, so the first point is at 4, 4, and we have a vertical line there. And so then let's do another point at 7, 7. So it's going to be a triangle like so. And we're going to drop this down to 2. draw a little rectangle here. And then from 8 to 12 is going to be a semicircle. So it's a very geometric shape here. So from this geometric shape we can find all kinds of areas. Right? So let's go ahead and find the area from, or let's find the integral from 4 to 7. So I want to find the area from 4 to 7. So it's basically this trapezoid here. And so if I were to break this apart, I'd probably break it apart as a square and a triangle. Right, and then the area of the square has a length of 3 and a height of 4. And so that makes it a total area of 12. And the triangle has a base of 3 and a height of 3. And the area then would be 1/2, 3 times 3, so 9/2. Or 4.5, right? So I'm going to get, let's change this to 24 over 2. So I'm going to get 33 over 2, right, as that area. So then let's go ahead and find the area from 7 to 12. Oops, good grief. From 7 to 12 of f of x dx. All right, so the area from 7 to 12 is the area of this small rectangle and this half circle. Okay. So the area of this small rectangle, it's a 1 by 2, so we're going to get an area of 2. And then the area of this half of a circle, the radius is 2, right? So we're going to get pi r squared. Right, so 4 pi plus 2. And I'm just going to leave it at 2 plus 4 pi. Right? So then let's go ahead and find the total area from 0 to 12. So when we find the total area, I can split this to the integral from 0 to 4 plus the integral from 4 to 7 plus the integral from 7 to 12. And I already have the answers for the integral from 4 to 7 and from 7 to 12. So the only thing I need to add to that is the integral from 0 to 4. Okay, so 0 to 4 is a nice square, a 4 by 4 square, and so we're going to get 16. Okay, so the total area, 16 plus, I'm just going to put 16.5 plus 2 plus 4 pi. Okay, so I'm going to get 32.5, 34.5 plus 4 pi. I hope I did my arithmetic right. Okay, but if we were to calculate the whole area, maybe we do a decimal, maybe not. But you can find the area under the curve geometrically when possible. So that's it for 4.8. And I will see you guys later.